Welcome to Haber School of Advanced Chemistry. Haber cycle is the application of Hess's law. Enthalpy change of the direct route is equal to the sum of enthalpy changes in indirect routes. Haber cycle is basically drawn to find the value of enthalpy of lattice energy. Almost 5 types of enthalpies are involved in the construction of Haber cycle. Enthalpy of formation, enthalpy of atomization, enthalpy of first ionization energy, enthalpy of electron affinity, and enthalpy of the lattice energy. It is basically an energy scale diagram having the different enthalpies. There are two main routes, one is direct and other one is indirect route, and both routes start from the elements. Let's start the Haber cycle for sodium oxide. First, it is wise to find the oxidation state of each element in the compound. For that, you are going to draw a Haber cycle. For example, in this case, sodium and oxygen. So, in the compound, sodium is showing 1 positive charge or oxidation state, and oxygen is showing -2 oxidation state. Simply it means we will change sodium element to the sodium positive ion, and similarly oxygen element will be changed into the from oxygen element to the oxygen 2 negative ion. Draw a vertical line arrow labeling E enthalpy. Draw a horizontal line at the bottom to show the enthalpy of the element that is equal to 0. First, draw a downward arrow to show the enthalpy of formation of sodium oxide. This is known as direct route. Now come towards indirect route. 2 mole of sodium solid will convert into 2 mole of sodium gas. That is known as 2 mole of enthalpy of atomization of the sodium. Then 2 mole of sodium gas will convert into the 2 mole of sodium gaseous ion, 1 positive. So this is 2 mole of enthalpy of first ionization energy of the sodium. That's all about for the sodium ion. Now it is turn for the oxygen. First oxygen will atomize. Then there is the enthalpy of electron affinity. First electron affinity. Then second electron affinity of the oxygen. That is also known as electron affinity of O1 negative ion. This is the final destination of the oxygen or oxide ion. These two gaseous ions will combine to make a lattice known as sodium oxide, and enthalpy change is known as enthalpy of the lattice energy. In this diagram, downward arrows are representing the exothermic reaction, while upward arrows are showing the endothermic reaction. Formula of the Haber cycle that we have drawn now, that is, enthalpy of the formation is equal to the sum of rest of all enthalpies including in this cycle. Let's solve a past paper question that is of October November 2, question number 2, part C. Use your cycle the following data and the further data for the data booklet to calculate the value of the lattice enthalpy of the sodium oxide. Given data is atomization of sodium, electron affinity of oxygen, second electron affinity of oxygen, enthalpy change of formation of sodium oxide, and enthalpy change of atomization of oxygen, that is equal to half bond energy of the oxygen. As you know, we have already drawn a Haber cycle and we have made a formula for the Haber cycle of sodium oxide. Just put the values of enthalpy of formation, enthalpy of atomization, enthalpy of first ionization energy of sodium from data booklet, enthalpy of atomization of oxygen from bond energy data, enthalpy of first electron affinity, enthalpy of second electron affinity, and after doing the simple mathematics, we can solve this equation, and answer is minus 2521 kilojoules per mole, the enthalpy of lattice energy. Remember one thing, experimental lattice energy of the sodium oxide is higher than that of the calculated, because this is the calculation where we are only counting the ionic forces in the lattice, not the covalent one.